Good morning to all. Today we are going to discuss a review paper entitled as Advance in Glycoside and Oligosaccharide Synthesis. So, in this paper, we are going to discuss what is the need of the development of the glycosylation and the glycosides, because most of the glycans present in the biomolecules presently in the majority of the earth biomass. Those glycans connect by the glycosidic bond, and those glycosylation can be driven by number of factors. Because if you see the glycans present in the biomolecules have different composition of the sugars and the stereochemistry, and those stereochemistry and the composition can be achieved by the modification and the monomer glycosides. And once we have the glycans or the glycoconjugate, that can be utilized for the several biological applications. For example, the glycans protein interactions, and that can be developed, that can be lead for the development of the vaccines and other chemical biological tools. If you see here, in fungi and algae and bacteria, if you see the monomer sugar, that is the only mannose. But case of fungi, the connection is alpha 6 or the alpha 3 in the linear and the branch way. But in case of algae, all the managed unit are connected by the beta with a C3 hydroxy group. In case of bacteria, the connection is between 1, 2 and 1, 3 alpha fashion. So to achieve this stereoselective with the different position of the hydroxy group, that need several modification to start with the monosaccharide. So, and development of these glycans have major role in the environmental and the material and the health research. In case of protein and the nucleotides, so there are a number of way to get the selective proteins and the nucleotides, because for that there are a number of way to go with to get the desired proteins. But in case of glycans, still there are a lot challenge to come out because of the different heterogenic and the different monomeric sugar units. If you think for the enzymatic way to synthesize the glycans, there are very limited way to synthesize the glycans, because those are very specific and those can be target only specific glycans. If you think for the polysaccharides, that can be cleaved out in the like oligosaccharide, but that oligosaccharides, there are number of oligosaccharides, then again there will be need of the purifications. So how to come over? There will be that can be divided in the 3 parts, like composition, connectivity, and the configuration. So the composition of the monosaccharide is nothing but like the orientation of the hydroxy group in the monosaccharides unit. For example, glucose and the mannose, these are the epimer, where the just one hydroxy group is differ from the one sugar to other sugar. By changing just one hydroxy group, that will completely change the outcome of the if there will be one monosaccharide that has number of hydroxy group, each hydroxy group has different reactivity, and that can be undergo for glycosylation with the different monosaccharide at the different position. And also not only glycosylation, that hydroxy group can be converted into the glycosidic sulfates or the acetate or in the acids. So for that, there will need to be a very selective protecting group or the proper manipulation for the chemical steps. The third one is the configuration. how configuration will help. So in configuration, like if we'll discuss about the cellulose and the amylose, so both are 1,4 glycosidic linkage, but one case the cellulose is beta 1,2 translink that provides strength of the plant cell, and other case that is the amylose alpha link 1,2 6 that is function as the energy storage molecules in the plants. Just there is a, if you see the connection is 1,4, but just changing the stereochemistry or the link that change the complete functional. So we need to have proper control in the configuration of the at stereogenic center. So here we can see the glucose and the galactose just changing one hydroxy group orientation, and the connectivity lead to the different sugar here, beta 1,4, beta 1,3, and the connect configuration alpha and beta. These collectively can be modified by number of way. There are a lot way to discuss and control those composition, connectivity, and the configuration. So here we'll be discussing about the general mechanistic aspect of the glycosylation, which lead to the configuration, and also glycosylations reactions and the method of glycosylation, and some recent and the complex glycoside synthesis. If you see the glycans composition, they have different monomers of the sugars. Generally, if you see the bacteria, they have a lot rare sugars. Those are not commercially available in the nature. Those cannot be simply modified in the protecting group. Before that, there will be modification in the orientation of the hydroxy group, or the even the need to be changed the functionality as well. So like if you see some of the sugars does not have even hydroxy group also to first L-fucosamine. So where you need to install the amine group, and some of them you have to remove the hydroxy group to make it deoxygenated sugar or the anhydrous sugar. So achieve this monomer, there are a lot method to do. Here, there is one way to just modify the just monomer. That is the photochemical way, where people have used 4% of 4 CBZPN, that is the 1,2,3,5 tetrakis carbazole 9L for 6 dicyclobenzene, as well as quinidine 10%, 10 mole percent of quinidine, 50 mole percent of adamantone thiol, and 4-chlorobenzoate, ammonium tetrabutyl ammonium salt of 4-benzoate, 4-chlorobenzoate in acetonitrile dimeso. So in that case, starting with the methyl glucoside, there will just 3 hydroxy group was coming equatorial to axial. So there are a number of sugars has been done. Just they have converted one hydroxy group to another, just minimum protecting group or just modification at the anomeric group. These kinetics, this reaction undergoes via the hydrogen atom abstraction or the hydrogen atom donation. Once this monosaccharide will be formed or will be there, that can be utilized for the glycosylation to get complex uh, glycans or the rare sugars modification in the glycose conjugate system. Second one is the glycan connectivity. The glycan connectivity, there are still a lot challenges because each hydroxy group has to be react with the in presence of other hydroxy group. To do so, there are a lot protecting groups are there, or to orthogonally can be protect and deprotect in the systems. And those protecting groups can be work for the monosaccharide as well as the oligosaccharides. So what will happen in the protecting group? That protecting group will mask or one half the hydroxy group or the which the number of hydroxy can be needed to protect. And further, that after the glycan, that protecting group can be cleave out in the selective fashion, or the complete removal of the protective group will lead out the complete glycoconjugate or the glycans. For example, benzalidine group can be installed, and after the one modification that can be reduced selectively open under the reductive condition, either C4 hydroxy, free hydroxy, or the C6. Then again, that can be utilized for the further glycan synthesis. And other way, one part protocol is dibutylene oxide or diaryl boronic acid that reduces selective acyl or the alkyline of the one of the hydroxy group present in presence of the multiple hydroxy group. Again, those free hydroxy group can be further utilized as a glycoconjugate synthesis. So these are the protecting group for the hydroxy group and the amine nitrogen for the amines sugars. So each and every protecting group will lead out to the for the stereoselectivity and the orthogonal protecting group that can be modified uh, or installed in between or after the glycosylation. The normal glycosylation, where there will be one glycosyl donor and other one will be the glycosyl acceptor. In presence of glycosylating promoter, the glycosyl donor will form as a electrophile or the oxocarbenium. Then within coupled with the nucleophile, that will lead out to the alpha or the beta stereomers. The stereospecific formation of the glycoside bond is a major synthetic challenge in the glycan synthesis. Still, for the 1,2 trans glycosylation method are now very much established, where the C2 hydroxy group play a major role, either through the NGP or the controlling the electronic at the anomeric position. But getting 1 to cis is still difficult. There are few methods, but still that can be modified to the further. If you see the proper like normal glycosylation in glycosyl donor in presence of promoter, that will lead out to the oxocarbenium ion, and that will be in presence that can be present in the several form like solvent separated ion pair or the beta contact or the solvent alpha contact ion pair. So these will lead out to the SN1 pathway for the incoming nucleophile. For the there are known for the immediate and the triplet where the alpha or the beta complete covalent bond formation happened and characterized. That will lead out to the SN2 ejection. So now this directness is fixed. Now the incoming nucleophile can come either one side, either alpha or the beta, as presence of the living group. So SN2 mechanism is very much established till now. There are, but case of SN1, there is still lot more characterization need to be done to say whether which pathway, how this stereochemistry getting controlled. As I've told you, for the C2 participation and the like triplet at the immediate has been like characterized in the low temperature NMR, but which lead out to the SN2 mechanism. But for SN1, there is still modification need to be done. But there are some reports where people have suggested how this stereochemistry getting controlled in case of SN1 mechanism too. So this glycoside bond formation, there are there are several way to like modify or the which affect the outcome of the glycosidic bond. But still, since this depends on the a lot factors, so it's very complex to uh, come out. This is the only way. This is the factor only affecting the glycosylation or the outcome of the stoichiochemistry of the glycoside product. So if you see here, there are living group, acceptor, donor. That is the permanent means this will be there. Without this, there will be no this thing needed, as well as the environment of the glycosylation where the temperature can be alter the outcome, activator, concentration, solvent, and how much water can be tolerated in the glycosylation where the hemiacetal will not form, and the influence also the stability of the intermediate and the protecting group and the living group, and the mechanism, which mechanism the reaction is following. If you see the in case of mannose, the alpha monomer is very much favorable because of the anomeric effect. And similarly, beta glucoside is very much established because of the NGP. But case of alpha glycoside, that is completely depend upon the thermodynamic factor. That is the stability of the product. But in case of beta monoxide, that is still not reliable whether that depends upon the thermodynamic factor or the anomeric, because here there is no anomeric like the stability of the outcome of the glycoside product. So getting beta glycoside is still very challenging. And also the anomeric glycosidic agent also matter a lot. For example, if you're having the thioglycoside at the non-reducing sugar, any point of time that thioglycoside can be converted into the number of different donor. That donor can be further utilized for the glycosidation. In case of thioglycoside, it can be converted to hemiacetal by using NBS and can be converted to fluoro by using dust, and that itself can be activated by using any of the thiophilic activator, and also by using the NIS and diabetyl phosphate, it converted with phosphate donor. Then again, phosphate donor can be converted to the final glycoside, and also this thioglycoside can be converted to bromide, and then bromide can be converted to the glycoside. So this modification can be done initially or the after the number of the glycosylation, that is oligosaccharides. And the choice of solvent is also matters in the glycosylation. For example, poor solvents with the poor electron properties like lithium and the toluene implied in the glycoside synthesis because they promote SN2 type, because that will not stabilize or there will be no complete coordination between the intermediate. But solvent having electron property like ethers, dioxane, acetonitrile, that will lead out to one of the selective way, like either alpha or the beta fashion, that will give out only one stereochemistry. For etheric solvents, those are alpha directing group, and the acetonitrile, that is beta directed group, because in case of acetonitrile, there will be one axial bond formation with the acetonitrile where the nitrogen lone pair will attack on the anomeric carbon, and it will form the beta linked glycoside. Then incoming nucleophile will come, alpha nucleophile. Incoming nucleophile will come through the beta fashion. In case of etheric, that will give the alpha product because they will coordinate with the beta fashion or the mass beta. So the incoming nucleophile will come through the alpha way. In case of DMF, that will form the immediate in the alpha fashion. So since now this alpha phase is blocked, the incoming acceptor or the nucleophile will come from only uh, beta function. So outcome will be the sorry. So here this alpha is immediate is stable. So it will the only beta immediate will react to give the alpha glycoside. So here this way, this 1,2,6 glycoside can be formed with the DMF. Since here the alpha immediate is measured, so this reaction will take time, and also it will be very slow reaction because the alpha will be very much stable compared to the beta, and beta only give out the product. Temperature also manipulate the reaction outcome. Uh, as we know, like since we're doing the glycosylation reaction, this glycosylation reaction used to be done at low temperature, below or the at room temperature. But there is exception to for the synthesis of Shigella flammary oligosaccharide, where temperature need 75 degree for the effective glycosylation. Other than this glycosylation, um, mm, majority of the glycosylation have been done or been doing at lower temperature. And the low temperature always facilitate the steric SN2 type reactions, and the lower temperature give beta glycoside compared to the alpha. And also the reaction, glycosylation reaction at lower temperature, that will minimize the side product, and also the stereochemistry will be controlled at the lower temperature. Now we'll discuss the protecting group. Um, as we know, the monoglycoside, each and every hydroxy group had different reactivity. If you consider 1C4 conformation of the any glycoside, any monosaccharide, the C6 will have here this the glycosyl. C6 will be having most reactive other than the anomeric. Then C3 hydroxy will come, and then C2. The least reactive is the uh, C4 hydroxy group. And also the compared to the axial and the equatorial hydroxy has more reactivity compared to the axial one. If you see this reaction scheme, there is two hydroxy group present, equatorial and the axial. So here the equatorial hydroxy group undergoing for the glycosylation, even with the very good selectivity, 79% yield in presence of C4 hydroxy group. In the glycosyl acceptor with the NGP in equatorial, so neighboring alcohol in equatorial position are more reactive than the acceptor. Like if we discuss about the 3-hydroxy of mannose versus glucose, the glucose 3-hydroxy is mannose 3-hydroxy more reactive than the C3 of the glucose. And also the ester protecting group that will withdraw the electron from the ring, so that will disarm the reactivity and that will give the like control the stereochemistry. But in case of the electron donating like benzyl group, in that case there will be always a chance of getting mixture of the alpha and beta. And also nucleophility of the acceptor affect the glycosylation stereochemistry. And also reactivity of the nucleophiles. If the nucleophiles is less reactive, that will give the selective either alpha or the beta glycoside. So reactivity and the protecting group, these are matters for the outcome of the glycoside products. As we know, the C4 hydroxy group of the glucosamine is the least reactive, and that can seen in the more of the glucosamine case, where people have took the challenge and where they have taken the auxiliary ring, where the C2 and C3, 2-amine and C3 hydroxy group undergo protection, that will uh, lead out to the more reactive C4 hydroxy group, because of there will be reduce the steric hindrance. For that, people have taken the chitin oligosaccharide, where they have taken different protecting group at the C2. The final protecting group what they have used, that is the CBZ and the N-trichloroacetyl. In those cases, they got good yield with the phosphate donor. Even compared to thioglycoside, in they were getting the 8%, but in case of phosphate donor, they were able to achieve 34%. So where they have taken different sugars and the different protecting group, with respect to modification, they got different yield, different percentage of yield with the phosphate donor. And the protecting group at the neighboring hydroxy group also alter the reactivity and the stereochemistry. Here, the synthesis of the Pseudomonas aeruginosa OL11 antigen. In this case, this naphthyl group near to the this hydroxy group, C4 hydroxy group, if they have took acetyl allyl, in those cases the yield was very poor and the stereochemistry was not good. Once they have taken the naphthyl methyl protecting group, in that case they were able to achieve 84% yield, and that reaction was even done at lower temperature. So in that means the protecting group also alters the reactivity as well as the stereochemistry outcome. Protecting group influence the reactivity of the glycolytic agent and the stereochemistry of the outcome, glycosylation outcome, and also inductive effect like benzyl ether stabilize the intermediate, and then that intermediate can be done at the SN1 or SN2 fashion to give mixture of the glycoside. And the protecting group also alters the reactivity and the stereochemistry. For example, the ester group present and different position can alter the reactivity and also the outcome. But in case of it like ester group, they reduce the reactivity, and after the once the reactivity will be reduced, the glycosylation rate will be slow, and that can be that utilization will be very less. But the ester group can be that can be remove presence of any other protecting group. So people have used still using the ester group protecting group, and for that people are doing some kind of other modification in presence of ester that can be tuned. Electronic effect also matters the glycosylation. Like if you are having the E3 group, that will increase the electron density of the ring and arm the sugar, and that will um, can be can be activated at the very mild condition. And in case of acyl group at the C2, that will give the 1,2 trans, but getting 1,2 cis is still uh, challenging. But in case of ester group, the C2 NGP is very much established. People has been have their faith. Okay, this is the only way to stabilize the intermediate. But ester group present other than C2, like C3 and C4. People still do doubt whether how this is the intermediate is getting controlled, even though there are a lot method where utilized, where this intermediate can be detect, and the mechanistic way can be say like this is the only way how this stereochemistry is getting controlled. For C2, there is no doubt this is the only way this diauxylamine ion will form, and the incoming nucleophile, the beta phase, alpha phase block, beta phase is only way to undergo for the glycosylation. But in case of C3, C4, C6, now there are a way to determine the intermediate either through the low temperature NMR or the IR, and also there are way like DFT. People have characterized this intermediate too, and these intermediate also give proper understanding of the outcome, how the stereochemistry is getting altered. Um, Having C4 and C6 O-bisphenol group, that will has steric as well as the electronic effect of the glycosylation, because if you think like this is the ether bond, but still it has steric effect, through that it will disarm the sugar uh, and also alter the anomeric effect. But generally etheric group give beta selective uh, glycans or the oligosaccharide synthesis. But to get alpha selective, there are a way where people have used very bulky group at C6 and the C4. So one of the example here for the to get alpha selectivity, that is the cyclic ditertiary butyl silylene DTBS protecting group, that will give out the alpha selective in case of glycosylation. If you see this example where this thioglycoside was converted into the immediate, that can be used NBS, again this trichloroacetonitrile, that will give the immediate, and that immediate was presence of another thioglycoside acceptor in the team triplet, that give the beta in case of here the C2 was phthalimide. Now this here, this DTBS protecting group, that is lead out to the alpha selective fashion. Even there is a ester group present at C2. Now this NGP has like like not dominating effect compared to this protecting group or the bulkiness of this tertiary butyl group matters for this glycosylation to get the only alpha exclusive alpha glycoside. So further we'll discuss the number of glycosides for the synthesis, which has been developed for the synthesis of number of oligosaccharides and the glycans, like Fisher, Helfrich method, halides, thioglycoside immediate phosphate and other organic and transition metal catalyzed reactions. Thank you.
Thank you, Via. Very good presentation.